Hey, 7th grade. So in this video, I'm going to introduce you to one of the foundations of algebra, and that is the topic of functions. This is going to be something that we're coming back to constantly over the next 2 years in Algebra 1 and in Algebra 2, and something you keep on seeing in your math classes throughout high school and college. Okay, you'll look at functions in pre-calculus, calculus, and beyond. And so even though we'll be doing a lot of complex problems involving functions, working with equations, graphing them. The whole idea behind a function is pretty simple, and that's what I want to look at today. Just what is a function and what do I mean when I use the word function in an algebra class. Okay, so let's go back to what we talked about in the last video, and that was the concept of relations. So if you remember, a relation, we said, is just a set of ordered pairs. And a lot of times you can see that set just listed as ordered pairs in parentheses, so a set of coordinates. You can see it listed as a table, as a mapping diagram, or as a graph. Well, a function is just a specific type of relation. Okay, so a function is going to look a lot like a relation, but it's got to have certain characteristics. Okay, so in order for a relation to actually be classified as a function, each input value, and if you remember, the input values are the x values, or we also call those the domain values. So each domain value must be paired with exactly one range value, and the range are also called the output values, or the y values. Okay, so a lot of different vocabulary words to represent the same idea. In order for a relation to be a function, every input or domain value has to be paired with exactly one range or output value. Now, when you first hear that definition, it doesn't really make a lot of sense, okay? So I think the easiest way to visualize this is to use a real-life example. So I'm going to talk about, rather than numbers for a second, I'm going to talk about a vending machine. So I want you to imagine that you're walking up to a vending machine that is stocked with candy. Okay, so we've got this vending machine right here, and it is stocked full of every single candy you can think of. Okay, and in that vending machine, you've got different rows with different slots, and a lot of times when you see a vending machine, those slots are going to be labeled with a letter and a number. So let's say this slot is A1 because it's in row A, this slot is A2 because it's in the second column, A3, A4, A5, okay, and that pattern continues on down. Okay, this would be B1, B2, B3, etc., etc. And in those slots, I want you to imagine there's different snack foods and candy bars. So let's say in slot A1, let's say you've got a Snickers bar. Let's say in slot A5, you have some Skittles. Okay, so let's say you walk up to the vending machine, okay, and of course you put in your money, and then in order to tell the vending machine, okay, and the vending machine here is going to be our input-output machine, okay, this is our function machine. In order to tell the vending machine what you want, you have to put in an input value, okay, and so that input value may be A1, okay, let's say you type in A1 as your input value. Well, if you type in A1 as the input value, then the output value is going to be a Snickers bar, because Snickers are in the slot for A1. Okay, so a vending machine is a real-life example of a relation. Okay, you type in A1 as your input, your output is a Snickers bar. If you type in A5, your output is going to be Skittles. So far I haven't really told you anything different from the last video. Okay, this is an example of a relation, okay, this vending machine relationship. But I want you to think about how a vending machine works. If someone else comes up to the vending machine and they type in A1, what are they going to get? Well, they're going to get Snickers. If the next person types in A1, they're also going to get Snickers. Every single person that types in this specific input here knows what they're going to get as the output. They're going to get Snickers. Every person that types in A5 is going to get Skittles. So every single time you go up to that vending machine, you know what your output is going to be, because every single input, that is every single code, only corresponds to one single candy bar. Okay? You can't have A1 going to Snickers sometimes and then canned sardines the next time. Okay? That would be a very, very, very bad vending machine. Okay? there shouldn't be any surprises when you're getting something from a vending machine. So that's what I mean by every single input value has to be paired with exactly one output value. You can't have a single input value going to multiple outputs. Otherwise, you're not going to know, okay, it's going to be random chance of what you might get as your candy bar. So I want you to keep that visualization in mind as we talk about functions. Keep this mapping diagram visualization in mind, because this is what you need to refer back to anytime you're trying to determine whether a relation, whether a set of ordered pairs, can be classified as a function. And so that's what we're going to do here on the first couple of examples. I'm going to give you some sample relations, just like we saw in the last video, and you're going to determine just whether or not these relations are actually functions. So this first example, I'm giving it to you in a mapping diagram. I have a list of names for your domain values and a list of genders for the range values. So take a look at this. We have Abby corresponds to being a girl, Alicia corresponds to being a girl, Ari as a boy, Barrett as a boy, and Cassidy as a girl. So would you say this is a function, yes or no? This answer would be yes. Okay, this one is a function, and that's because every single domain value only corresponds to one range value. Abby is only a girl, Alicia is only a girl, Ari is only a boy, Barrett is only a boy, Cassidy is only a girl. So because all of these x values only go to one y value, then this is a function. Okay, this mapping diagram here, your domain values are different months of the year. So I have April, February, and September. And the range values are different holidays. We have April Fool's Day, Easter, Valentine's Day, and Yom Kippur. This relation is not a function. And the reason it's not a function is because you can see that this domain value of April corresponds to two different y values. Okay, April Fool's Day is in April, and oftentimes Easter is in April. Because this input value goes to two different output values, we would say this relation is not a function. Okay, let's try that now with a set of ordered pairs. So in example 3, I'm given a set of 5 ordered pairs. I'm going to go ahead and list these ordered pairs in a mapping diagram. So my x values, or my domain values, are 2, 3, 4, 6, and 7. My y values, or my range values, I have a 7, and that 7 repeats. I have a 9, and I have a 10. Okay, so let's do our mapping diagram like we did in the last video. 2 corresponds to 7, 3 corresponds to 7, 4 corresponds to 9, 6 corresponds to 10, and 7 corresponds to 10. Okay, so is this relation a function? Well, at first glance, okay, a lot of you might say, no, this relation is not a function. Okay, because you see different input values going towards the same output value. But I want you to think back to what the definition of a function said. It said each input value has to be paired with exactly one output value. Well, 2 is paired with 7 and only 7. 3 is only paired with 7. 4 is only paired with 9. 6 only goes to 10, and 7 only goes to 10. So by that definition, this one actually is a function. Okay, you can have different x values going to the same y value. Just like in a vending machine, you could have a vending machine full of Snickers bars. Okay, every single slot here could be full of Snickers if Snickers are really popular. That would be okay. Okay, I could have A1, A5, B1 all going to Snickers, and that would still be a good vending machine because you know what you're getting every single time. So as long as every single x value only has one y value paired to it, then it is a function. Number 4 here, however, we're going to see is not a function. If I do the mapping diagram for this one, my x values are 2, 3, and 5. My y values are -5, -2, 1, and 6. So I see 2 corresponds to 1, 3 corresponds to -2, 5 corresponds to 6, and then 2 also corresponds to -5. As soon as I draw a second arrow, okay, from any of these x values, in this case it happened to be the 2, you know that that's not a function, okay, because each input can only have one output. 2 in this case has 2 different outputs, -5 and +1, and that is not allowed for functions. So this one is not a function. Okay, we have another way to determine whether relations are functions, and this little test, this is called the vertical line test, is useful anytime you're given the relation as a graph. Okay, so whenever you're given a relation as a graph, you want to keep this vertical line test in mind. What the vertical line test says is if any vertical line can be drawn through more than one point on the graph, then the relation is not a function. Okay, if any vertical line can be drawn through more than one point on the graph, the relation is not a function. So here's how that works. Number 5, I've given you a graph of a relation. Again, a relation is just a set of ordered pairs. So this graph is just a bunch of ordered pairs interconnected to form a circle. And your job is to tell whether or not this relation is a function. Well, if I can draw just one vertical line anywhere on this coordinate plane, and it intersects my graph in more than one spot, that means that the relation is not a function. You can see that there's a lot of different vertical lines to choose from. If I just draw a vertical line right here, I can see that that vertical line hits my graph, okay, my circle, in two spots. It hits it right here, and it hits it right here. Because this vertical line intersects the graph in two spots, this relation is automatically not a function. Okay, number 6, this is my graph. This sort of, we're looking S-shape here, okay? This graph right here, as many times as I can try drawing vertical lines, okay, I can draw an infinite number of vertical lines, and none of them are going to hit the graph in more than one spot. Okay, every single vertical line I draw here only intersects this graph in one place. Here, 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 and so forth. So this relation here is a function, again, because I can't draw a single vertical line that touches the graph more than once. Okay, moving on to the next concept, this would be function notation. So from now on, you're going to see equations oftentimes written with this symbol right here. Okay, and it's going to be an F and then in parentheses an X. This symbol right here, first of all, does not mean F times X. Okay, it does not mean F times X. This is simply a symbol to represent the output of a function value, and we call this function notation. So a lot of times you're going to see function notation written with this symbol. Sometimes you'll just see it written with the variable y. And both of these symbols, both y and, again, this symbol f of x is how we read it, just represents the output of a function. Okay, it represents the range value of a function. So I want you to get used to seeing this symbol right here. Again, it does not mean times, okay? It's read as f of x, and it's just a way to represent the output of a function value. So now we're going to practice using that symbol in these next few examples. So in each of these examples, I'm going to evaluate each function based on what I'm given. So let me show you how this works. Number 7, I'm given the equation. Again, I read this as f of x equals 2x plus 1, and I'm supposed to find f of negative 2 is how I say this. All this means is it wants me to take this equation, it wants me to use an input of negative 2. Okay, so this is my input value, and it wants me to determine what the output would be. So to find the output, we're going to take negative 2, and everywhere we see an x, okay, we're going to replace the x with a negative 2. So f of negative 2 would be equal to, my equation is 2x plus 1, so I'm going to take my equation and instead of x, I'm going to plug in or substitute a negative 2. So 2 times negative 2 is negative 4, plus 1 gives me negative 3. So that means that my output, okay, for this problem is negative 3 anytime my input is negative 2. And that, again, is what it means to evaluate a function. So for number 8, this time I'm given g of x equals x squared minus 4, and I'm supposed to find g of negative 3. Yes, sometimes they'll give you g's or h's, okay, instead of f's. That's still function notation right here. So all that means is I need to take negative 3 and I am plugging in -3 anywhere I see this variable. In this case, this is an x. So x squared minus 4, okay, is the other side of my equation. So I'm going to take -3 squared and then subtract 4. Well, -3 squared is positive 9, and then 9 minus 4 gives me 5. So 5 is my output for this function. Okay, number 9, my function rule is h of x equals 3x minus 4. I'm supposed to find h of 5a. Okay, well, this works the same way as it did in the examples above. Okay, so I'm going to take my input they're giving me, which is 5a, and I'm going to plug that input in everywhere I see this x. So my equation, h of x equals 3x minus 4. Instead of the x, I'm going to plug in a 5a, and now I'm just going to simplify. 3 times 5a would be 15a, and then I just have this minus 4 over here on the other side. So my output here is 15a minus 4. Okay, number 10, I have h of t equals -5t cubed plus 2t. I'm supposed to find 3 times h of n. Okay, at first this one's going to look a little tricky, but again, it's working the same way. So first of all, I'm going to ignore this 3 for a second. Let's just focus on this h of n value. All this is asking me to do is it's asking me to take my function, h of t, and it's asking me to plug in an n instead of a t. So it's going to look like this. H of n is going to be equal to -5 times, again, my input value is going in place of t. So I'm going to put an empty set of parentheses where those t's were up here. And I'm just plugging in an n instead of t. So this really isn't too exciting. All you're doing is replacing t with n for this. So you get -5n cubed now plus 2n. Okay, now let's take a look at that 3. All it wanted us to do was multiply everything by 3 at the end is what that means. Okay, 3 times all of this. So if I put in this 3 now, and I take everything here times 3, that just means I need to distribute this 3. So 3 times -5n cubed would be -15n cubed. 3 times 2n will be 6n. So the output here is -15n cubed plus 6n. Okay, my final example I have for you is I'm giving you another function rule. This one is f of x equals -1/2 x minus 6. And this time I'm giving you a domain, okay, a list of domain values. Those values are -2, 0, and 5. And what I want you to do is I want you to find the range for this function right here. Well, if I give you a set of domain values, okay, I'm just giving you a set of input values. So all that means is you're going to take each of these input values, substitute them into the function, and give me their corresponding range values, or the outputs. So basically I'm doing what I did up here in examples 7 and 8, 3 separate times. Okay, I'm going to plug in each of those input values just like I did in 7 and 8. I'm going to plug in -2, 0, and 5 3 separate times, and so I'm going to get 3 separate outputs. So I'm going to find f of my first input is -2. Then I'm going to find f of my second input, which is 0. And then I'm going to find f of my last input, which is 5. Okay, so every single time we're going to take -1/2 times the input value minus 6. Okay, and so let's start with this first one. We're putting in a -2 as my input. So -1/2 times -2 is +1. Subtract 6, I get -5. When I put in 0 as my input, -1/2 times 0 is just 0. Subtract 6, I get -6. Okay, and then when I put in my last input 5, negative 1/2 times 5 is negative 5 halves, or negative 2.5. Minus 6 would be negative 8.5. So you have three different range values here. You have negative 5, negative 6, and negative 8.5. I'm going to describe those just like we did in the last video as a list of numbers in increasing order. So negative 8.5 would be the smallest, then negative 6, then negative 5, and I'm going to place them in braces. Okay, so a lot of new concepts in this video. Okay, I realize some of them may not be clicking right away. That's okay. We'll practice this the next time I see you in class. Until then, have a nice day. You are all wonderful people. Take care.